Welcome back to Chapter 18, Part 3. We're going to continue on with looking at hypothesis testing for two-sample independent case. First, let's take a look at what the null and alternative hypothesis for Chapter 18 problems would look like. The null hypothesis is going to look like this, that we're going to assume that mu1 minus mu2 equals 0, or we could write that as, just by simple algebraic manipulation, that our null hypothesis is that the two means are equal. So we're always going to assume that they're equal. The three alternatives will look like that we think that mu1 is greater than mu2, which translates to what we see here first, that mu1 minus mu2 is greater than 0. So again, you could write that right-tailed test either one of these ways. They're exactly the same. The second would be our left-tailed test, mu1 minus mu2, their difference is less than 0. Or, again, another way we could have written that was mu1 less than mu2. And then the third case, where they're not equal to one another, mu1 minus mu2 doesn't equal 0. Or alternatively, could write that the two means just don't equal each other. Now, with that in mind, let's take a look at the test statistic for that problem. Well, if we wrote the test statistic, we'd get that x1 minus x2, that is our statistic for the difference of two means, minus our null hypothesis value, which is mu1 minus mu2. But like I said, in Stat 250, we're always going to assume that that's 0. This is not the case always necessarily, and in fact, when you get into upper-level statistics in real life, it may not be the case at all. But in our class, we're going to always assume that that value is 0. So we can simplify our test statistic to look like x bar 1 minus x bar 2 in the numerator divided by the standard error. And we have to remember, for all of our hypothesis tests, what's the criteria for rejection? For any hypothesis test that we do, we would say, if the p-value we get is less than alpha, we're going to reject the null hypothesis. And remember what the p-value is. It's where we take our test statistic and we determine what the probability is that we could take another sample of that same size and would be further out in the tails than where that statistic lies. Our p-value is the probability of a type 1 error based on our sample. So now it's time to take a look at an example. So we're going to look at this case study of exercise and pulse rate. A study is performed to compare the mean resting pulse rate of adult subjects who regularly exercise to the mean resting pulse rate of those who do not regularly exercise. So we have 29 people who exercise. We take their mean resting pulse rate and we get a sample standard deviation. We do the same for the non-exercisers. We have 31 in our sample. The mean was 75 with a sample standard deviation of 9. This is two samples that are independent. One big giveaway is that our sample sizes aren't the same. And the exercisers we pick had nothing to do with the non-exercisers. So there's independence here. We'll assume that the subjects were picked by a simple random sample, and our sample sizes are large. Although the exercisers are only 29, we're just going to assume that it came from a normal population. Now, the way that we would get our confidence interval is in a 95% confidence interval, is we've got our sample means, but we have to figure out our critical value. Well, the critical value is we're doing for a 95% confidence interval, but how do we find the degrees of freedom? Well, let's go back a slide and we look for the smallest sample size, which is 29. So our degrees of freedom should be 28 if we're using the conservative method, and that's what we're using. So look at Table C. If you look at the 95% confidence level with 28 degrees of freedom, the critical value is 2.048. Our standard error is the square root of that sum, 9 squared divided by 31 plus 86 squared divided by 29. When we do the calculation, we can get our 95% confidence interval. And one way to interpret it would be this. We are 95% confident that the difference in mean resting pulse rates between non-exercisers minus exercisers is between 4.35 and 13.65 beats per minute. Now in your homework you'll be required to calculate one of these standard errors. Other than that, we'll give you the standard error. And for quizzes and tests, you will always be given the standard error for these two sample problems, because it just takes a little bit of time to calculate them. And we don't want you to waste that much time on the quizzes and tests. We'd rather you use that. Be able to use the standard error to get your confidence interval. Now if we look at that interval, it's an interval number between 4 and 13. That interval never contains 0. So it kind of tells us something about the mean resting pulse rates between non-exercisers and exercisers. If the mean of non-exercisers minus exercisers never equals 0, that means that they can never be the same. So we know something from our confidence interval if we look at it, that more than likely exercisers and non-exercisers won't have the same resting pulse rate. So let's take a look if we did the significance test. Now we have a good idea just based on that confidence interval that we're going to reject the null hypothesis, but let's go through a whole problem and see how we would do this. Again, we're looking at these pulse rates of non-exercisers and exercisers. We're now going to go through the procedure for doing a hypothesis test to write the null and alternative hypothesis. At a 0.05 significance level is the mean resting pulse rate of adult subjects who regularly exercise different from the mean resting pulse rate of those who do not regularly exercise. Now, the null hypothesis means that we're going to assume that they are equal, and the alternative is what we're looking for. At a 0.05 significance level, do they differ? So there's our alternative. And we can also know what the degrees of freedom are. We already figured that out. The smallest sample size was 29 for the exercisers. So therefore, our degrees of freedom are going to be 29 minus 1, or 28. So we resume doing our hypothesis test. We have our null and alternative. We know our significance level is 0.05. Now it's time for us to do our test statistic. Well, all we have to do is find x1 minus x2, which was given to us as 75 minus 66, divided by that standard error. And we get 3.961. The p-value we could get from capturing the alpha, or capturing the percentage, but we used technology. We used MINITAB and we got 0.000207. So the p-value is smaller than our alpha. Our alpha was 0.05. So we're going to reject the null hypothesis. So at a 0.05 significance level, there's sufficient evidence to support the claim that the mean resting pulse rates are different for the two populations. So I said we'd use MINITAB, but how would we do that? Well, here's the command that you would use. So let's see for our specific example how we would use it. We'd put, it's called the 2t command. We do n x bar s, and we put it in for both samples, and in this case we said, let's look at the confidence, the 95% confidence interval first. And there you see it there, it's 4.45 to 13.55. It's a little bit smaller than the interval we got when we used our conservative method for degrees of freedom and did it by hand. And we expected to do that, because look at the degrees of freedom. They decrease quite a bit when you use your conservative method. That's why you get the bigger intervals. So MINITAB is more exact, and so our intervals will be more precise. Here's the command we use to do our two-tailed test, and you see our p-value is 0.000, and in MINITAB the way we would write that is we say the p-value is less than 0.0001. Very small, so we have sufficient evidence to reject that null hypothesis. So that concludes Part 3. In Part 4 we'll continue and we'll work a little bit on MINITAB.